Alright, let's get started with the solution to the first exam. The first question is about Hewlett Razor Company. In this company there are this process there are 6 steps, and the question that asks what's the bottleneck in the process, what's the capacity of the process, what's the direct labor cost, and what's the average labor utilization. As we always do, the first thing to do is make the process flow diagram. So in this process flow diagram there are 6 stations: A, B, C, D, E, and F. Alright, we have the processing time for the first station to be 44 seconds, second 40, 55, 60, 50, and 40. This is all in seconds for Razor. Now we can, using the processing time, we can calculate the capacity. The capacity is nothing but the inverse, given that there is only one worker in each station. 40, 1 over 55, 1 over 60, 1 over 50, 1 over 40. Now this is in terms of razors per second. Well, given that 1 over 60 is the slowest capacity, this station is our bottleneck. When we know that is our bottleneck, we can write the processing capacity, or the capacity of the process, is given by the capacity of the bottleneck, which is 1 over 60 razors per second. Well, given that the demand is infinite, the demand is unlimited, we know the flow rate, which is the minimum of processing capacity and demand, is also 1 over 60 razor per second. Well, now we are ready to answer any question. The question says, what is the processing capacity in razors per hour? Well, if the question had only asked what is the processing capacity, we would already have had the answer, which is 1 over 60 razors per second. But given that the question wants the answer in razors per hour, we have to figure out a way to convert from razor per second to razor per hour. Well, we can do that in the side. So we have razor per second, we have to get to razor per hour. So to get rid of second, we have second on the top, minute on the bottom. To get rid of minute, we have minute on the top, hour at the bottom. So we have everything we want. But to make it equal, we have to 60 here, 1 here, 60 here, 1 here. So minute gone, second gone. We have 60 and 60, that is equals to 3600. So our conversion factor is 3600. So 1 over 60 razor per second multiplied by 3600 will give us answer in terms of razor per hour, which comes out to be 60 razors per hour. So that means our processing capacity, another way to express this, is 60 razors per hour. So this and this is equivalent. The next question asks, what is the direct labor cost associated with producing one razor? The formula for direct labor cost is nothing but wage divided by flow rate. Well, wage is easy. We pay $25 for 6 workers, which comes out to be 150. Now the bottom is given this 150 is in terms of dollar per hour. We need the flow rate in terms of hour, razor per hour. Well, when we saw, it's very easy to see it that the processing capacity is 60 razors per hour. That means flow rate must also be 60 razors per hour, because when the processing capacity was expressed in terms of razor per second, when the processing capacity is 1 over 60 razor per second, the flow rate was also exactly 1 over 60 razor per second. That means flow rate must also be 60 razors per hour. Now we have hour match, so that's why 150 divided by 60 comes out to be $2.5 per razor. Well, the next question is what's the average labor utilization? For this, we need cycle time. To calculate the cycle time, which is the inverse of flow time, which is 1/60 razor per second. Why do I want to use the one which has units in terms of razor per second? That's because all our processing time is in terms of second. Given that our flow rate is 1/160 razor per second, the cycle time, which is the inverse, is 60 seconds. If our cycle time is 60 seconds, our idle time is going to be 60 minus 44 is, so 60 minus 44 is 16 for the first one. Similarly, it's 40 for the 20 for the next one, 5, 0, 10 and 20. So this is for A, this is for B, C, D, E and F. All we did is we took the cycle time minus the processing time. We add this all up, we get 71. Similarly, we can add all the processing times and we get 289. Now we are ready to use the formula, which is just the total processing time, that is 289 divided by 280, the same processing time, plus the idle time of 71, comes out to be 289 divided by 360. This is equivalent to about 80%. Alright, we're ready to move on to the next question. The next question is a lot easier than it looks in the first place. The first part of the question is, well, recognizing what this is a little flaw question, so recognizing what is the inventory, what is the rate, and what is the flow time. It's easy to see that it's the 10 customers is inventory, because every time you go to the store you see 10 people there. So if the customer is the flow unit, that must be the inventory. So I equals to 10 customers. Similarly, T, the flow time, is 3 minutes. So we can calculate, we can use the little slope. I equals to RT, where I equals to 10, R is what we want, T equals to 3 minutes. So R equals to 10 divided by 3. So the interesting thing here is the rate is in terms of customers per minute. But remember, that's not what we want. We want how many people pass in that 3 hours, not that in 1 minute. In that 3 hours, so 3 hours is equivalent to 180 minutes. So all you gotta do is 10 divided by 3 multiplied by 180. So in that 180 minutes you have 600 customers. The next question is exactly what we did in the class. In fact, it's made even simpler. So in this question, so there is grilling station, toasting station and wrapping station. The available time for grilling is 60 minutes because there is only one worker. For toasting is also 60 minutes. Wrapping is 150 minutes because there are 3 workers, but one guy spends half of his time texting his late friend. Alright, that means how much is demanded? Well, it's a grilling. So there are 25 vegetables, 25 into 2, 25 into 2 plus 15 into 1, 15 multiplied by 1, which comes out to be 65. For the toasting station, it is 25 multiplied by 3 plus 15 multiplied by 2 comes out to be 105. Here it's 25 times 4 plus 15 times 5, this is 175. Now we can calculate the implied utilization. Implied utilization, that is just what is demanded divided by what is available. So that is 65 divided by 60, 105 divided by 60, and 175 divided by 150. This comes out to be 1.08, 1.75, 1.17. All of these are more than 100%, but this is the most constrained one, so this must be the bottleneck. Alright, in this question, the question gives us revenue, and it gives us inventory, and it asks us what is the turnover rate, what is the inventory turn. Remember, we can't use revenue, we have to convert that in terms of COGS. So how do you convert that into COGS? Well, we are given the ratio of the COGS versus the sale price. So suppose the total COGS is X, right? So if it cost you X dollars to make it, you sold it in 60 million. Similarly, equivalent is you produce something in 1250, you sold this in 2000. Well, then we can use the simple math here. Whatever the ratio of 1250 to 2000 is, the same ratio exists between X and 60 million. If you solve for this, X comes out to be 37.5 million. Okay, all you have to do is cross multiply and you should get there. That now we know COGS, we know the inventory. Then inventory turn is pretty simple. So inventory turn is COGS divided by inventory. So that is 37.5 million divided by 20 million. This comes out to be 1.875. So this is our inventory turn. Next question asks, assume the company has a 25% in a cost of inventory. That's the inventory cost is 25%. What is the inventory cost of the inventory cost of the product that cost it $12.50 to make? Okay, so let's calculate this in terms of percentage. If all we need is a 20 percentage, it would be 25% divided by the inventory turn, that is 1.875, comes out to be 13.33%. But it's a 13.33% of what? The COGS of the product, that is $12.50. So 13.33% of $12.50. So this comes out to be about 166.66. Well, that means that is the per unit inventory cost for the product. This question is a lot easier than you think. I expected most people to get this right, but there are quite a few errors. The question asks, throughput time, the time it takes from you to enter the system and to come out of the system, cannot be reduced. Cannot be reduced. Let's see. Reducing the utilization of the bottleneck. Well, that should help, because if you reduce the utilization at the bottleneck, the products will flow faster. They will have to wait in the queue shorter and shorter, so the product will flow faster from the beginning to the end. So this is obviously not the right answer, right? Throughput can be reduced this way. Changing the sequence of the activity, this probably tricked most of the people. Changing the sequence of the resources doesn't change it, but changing the sequence of the activities might change it. If that would also mean changing the to whom the activity is assigned. Suppose we have, say, 4 activities, 5 seconds, 10 seconds, 15 seconds, and say another 10 seconds here. So if we have 3 workers here, and let's make this 15, and then let's make this 5. Sorry. So now if we have 3 workers, and if we had one guy working this, another guy working this, another guy working this. Okay. Now we change the sequence of the task and make it 15 here, 10 here, 5 here, and 15 here. We've changed the sequence, and if we assign worker this way, then that might change the flow time. And this example might not be the best one, but you should be able to see that if we change the sequence of the activities such that the bottleneck is changed, the work assembly is balanced, then that would reduce the throughput time. So this is not a good answer either. Reducing interruptions, that is as obvious as it can get. Where you reduce the interruptions, the throughput time would be reduced. So all the above are the ways, in fact all the above are the only ways that we have learned in this class that will reduce the throughput time.